Hello, it's Mr. Nedick. It's about 9:40 p.m. on Tuesday, April 16th, or about 3Z on the 17th. We're looking at our first kind of appreciable severe weather risk this year, so I thought I'd quickly go through why that exists. So this is, you're looking down on the pole. Here's the United States, over here, here's Africa and Europe, and here's like Siberia. And so you're looking down at the jet stream, and you can see there's ridges and troughs, kind of ups and downs that rotate around this. And this is the one we're looking at here. This dip here, you notice even in the global scale is a pretty big dip. And that dip has something going on with it. It also has some high wind speeds in it. So the jet stream around it is pretty slow, only about 60 miles an hour. But inside of this little dip, the speeds are higher. Okay, it's called a jet streak. And the combination of this trough plus the jet streak is enough to create a low at the surface. So here's the low's position now. And as we kind of step through the day, that low will go forward. So this would be the position tomorrow at 1 p.m. You can see the southerly winds here, showing warm moist air from the Gulf, and then you've got northerly winds behind it, kind of as the wind spins around this low. There's also like these kinks in the isobars here, right? This little tip here. And what this is a cold front. You can notice as I bring my cursor through here, the winds seem to change direction where that little point is, right? And that front is the focus of our weather. And if we look at 18, so this is again right here, apologies, is 1 p.m. tomorrow, we can kind of see a front here, 77 back to 70, okay, kind of, but it's not very strong. But as the day goes forward, that front becomes more defined. Here's 60 to, 68, here 64 up to 70. So we start to get a little more defined front, this being 0Z 19, 7 p.m. And then kind of go forward another 10 p.m. The front becomes a little more obvious, but it's not a really, really strong like cold front where it's bitterly cold. You can obviously see the effects of the mountains over here. And so I'm going to show you a different number, which is called theta E, or the potential temperature, and kind of ignore what it actually means. It's a combination of temperature and dew point. You can see, okay, there's this relatively high area of theta E here. This is again at 1 p.m., 4 p.m., 7 p.m. And here that front becomes very obvious. You can see there's like kink to it, and then a bowed structure, and then down here across like the Red River Valley into the Arklatex, obviously very high values of this theta E business. And that's a result of moisture. So here's the dew point forecast at 1, at 4, at 7. You can see these moisture values are very high, 67-degree dew points. Here in Kansas City, even 65. And so there's a big difference. And it doesn't make a lot of sense, but actually moist air, wet air, it rises more because the molar mass of water is 18 and the molar mass of oxygen, let's say, is 32. So it's less dense because remember, Avogadro's law says that a gas occupies the same volume at the same temperature and pressure. So water, because it's got a lower molar mass, wants to rise. That's a big reason why clouds are, well, buoyant. You also see up here, way up in Iowa, there's a warm front. Here's the actual low at this time, and then the cold front, and some more circulation here from like a secondary low at the surface. So where this boundary goes is where we'd expect thunderstorms to fire, somewhere near it. So at 7 p.m., we'd be looking around Kansas City. So that's our forecast. I want to point out that computers don't always agree. So this is the same set of equations, more or less, giving a different answer. This is just a slightly different run of that model. And this is 1 p.m. You can see there's a hole. And that hole stays in place all the way through 0Z. Now, don't get me wrong, it gets better. It's still got really high dew points at this time of year, especially down here in Oklahoma. It's quite nice. But this is different than that, right? And these are valid at the same time, same basic math. And the question is, which one happens? If this one happens versus this one happens, we get different weather. The thing that's going to change about these is it's going to change how much instability. So again, looking at like 1 o'clock tomorrow here, 4 o'clock, 7 o'clock, we can see there's like a finger of instability along that front. And this is actually pretty unstable. That means for every kilogram of air you lift, you get about 2,000 joule. It's a decent amount of energy. And, if I look at different models, that changes, right? I don't have the same shape between these two runs. These are decently different. And the difference is this moisture variable. So one of these is probably right and one of them is wrong. They certainly both can be wrong, but they certainly both cannot be right. The question is, which does which? It matters because if I come in here and look at what's causing these things by probing it with a weather balloon, or at least a Madron, we see the problem. And that is between 1 and 3 kilometers up in the atmosphere, there's a warm nose here, right? This white dashed line is the path a cloud would follow if it would form. And here it's warmer than the environment, so it's going to rise, it's going to rise, it's going to rise, and then it hits this lid. It's called a cap or an inversion. And there's no buoyant energy. It's like the balloon hits a ceiling, right? And it can't go anywhere because it's warmer. So this model says, hey, there's a stopper on the thunderstorms. So I don't care what else is happening. There's something preventing this air from rising, which is a shame because if it could get up here, it'd be way warmer in the environment, want to rise a lot. And look how much drier the air is up here, right? This dew point line is way to the left of the temperature line, which means this parcel would really want to rise, but it can't because it's got a lid. You go over to a different model, and that lid's gone. The parcel starts at the surface, and whee, it's all the way up to the tropospause, right? It goes up 15 kilometers before it kind of finally stops. And this is what would cause a severe thunderstorm, right? This is a good sign. Now, if I look over at the winds, they're kind of a straight line. It's a really good sign that we're going to get splitting and straight line winds, and this isn't a good tornado setup. For tornado setup, you need to look more for curves in here, and this one's not bad. There's instability to be gained, and there's a little curve. This was actually pulled from Kansas City, so this is a forecast valid in our area tomorrow. And there is a marginal, at best, I really don't want to overstate it, risk of at least some rotation to these thunderstorms, although the risk is probably low, and based on the overall, I had to really cherry pick to find the sounding. The overall risk is really for straight line winds and severe weather, that non-tornadic. That being said, we can quickly pull up what the models think is going to happen. So 1 o'clock, 4 o'clock, 7 o'clock, 9 o'clock. Hey, those form just south of the city, right? So the question is, where do they form? If they form a little earlier, everywhere in the city gets hit. They form a little later, and they may miss only the whole city and only impact areas to our south, right? It's a very close line. And, I have lots of different computers that can simulate the radar. This is a different set of mathematical functions. Here we are, that fires them off at 7 p.m. over the city and brings them through. This is probably the most aggressive of the models. This is called the HRRR. It's probably the most aggressive of the models for our area tomorrow. Specifically, this little storm right here is really interesting. Yet other models, this is the WRF, which is what the NAM is based on, brings through. You can see the front here in this little thin line, brings it through without forming thunderstorms in any way. It kind of pops one up that just dies an hour later. And it really doesn't show thunderstorms forming until after nightfall, like 8 p.m., and more to our south. You can see there's kind of a Bowie structure here. That would be a straight line wind event, but again, it's to our south, and we shouldn't read too much into how the radar is actually simulated to look. And then you might go even farther to a slightly different run of the WRF, and this run does even less for Kansas City. Excuse me, let me go ahead and flip this over to loop. It's slow. I do this, and really nothing forms until here again, 8 p.m., and this is almost all the way to Wichita where they're forming, right? So it doesn't seem like that different. Like, oh, they all kind of show a line of thunderstorms, but really we're seeing a change from St. Joseph down to almost Wichita where the storms form, which is actually a pretty big area of disagreement. So tomorrow the question is, where's the front? And if the front hasn't come through yet, you still have a chance of thunderstorms. As soon as the front passes, your weather chances are over. And the reason why these models think it's going to happen is if I take a sounding in Kansas City, there's still a little cap. Now, front provides some forcing beyond just the cap. So, yeah, I don't know if I really buy them holding off until after nightfall, but we'll see. The big game tomorrow, though, is when you see the wind shift to a northerly wind right here, right? Then you know it's over. So if you monitor a weather station on the roof and you see, hey, the wind shifted to the north and there hasn't been a thunderstorm yet, you're not going to see a thunderstorm. But if the winds are still to the south, or from the south and light, well, you still have a chance of a thunderstorm. That's really as easy as it is to forecast. The positions are as it is. One last thing, I said that storm was interesting, so I went ahead and just put the storm tracks on radar using some more complicated stuff here. You can see this one storm moves a different direction than all these other storms. And so this storm here would be the one to watch for more rotation. If this were to perfectly validate, this would be the storm to chase. That'd be very conveniently short. But anyway, you can see that this area here is probably where we would issue a severe thunderstorm warning, or a watch, excuse me, and within them warnings. And some of the areas that are being highlighted for the best chance of severe weather, right now, at least in the model runs tonight, actually aren't showing that good of a detail. So my plan is to head out to kind of the Flint Hilly areas and chase it back home, and it won't be a lot of severe weather, but it probably is our first watch of the year, and but at least some lightning and maybe small hail and winds. Really nothing notable, no major violent tornadoes, no supercells or anything like that. At least that's what it seems like right now in the forecast, but still spring weather, that's worth talking about. So this isn't a great forecast discussion. It's not meant to be like an exhaustive example of how the weather forecasting goes. There's a million things I could have gone into more depth on, but that's more boring for everyone. But this is a decent overview of, like, if I want to just take a glance at what's going on meteorologically, what I do and how I determine, hey, is there actually a thunderstorm risk for our area? So again, in summary, yeah, probably towards the south of the city right now. Probably not until, let's say, 5, 6, 7, 8, 9 p.m. And as soon as the winds shift to the north, the thunderstorm risk is over. Probably going to see a severe thunderstorm watch. And yeah, probably still just a slight risk from the SPC. I can't really imagine this being enhanced based on what I'm seeing right now. Too many questions about the cap. So until then, I hope that was helpful too, and see you tomorrow.